Good morning, everyone. So I'm Robert Schumacher. I'm a developer at Microsoft working on CppCon, and today what I'm going to talk about is the things that we need to do to get over 1,000 libraries to build consistently against each other in our catalog. What I'm hoping that you'll be able to take from this is, one, you'll be able to gain an appreciation for how the sausage is made and how hard of a life that I have. But also you'll be able to take this on and you'll be able to write better libraries that are easier to integrate into systems like this. And if you manage a proprietary system like this inside of your company, which is unfortunately still very common today, then maybe some of these techniques will be of use to you to frame your thinking around how to work with those systems. So I'm going to go in three parts. First, we're going to talk about effectively what's the anatomy of getting a library, a single library, to build. Then we're going to talk about some ecosystem aspects of it. So when you scale out, how do these things interplay with each other and what you need to do to make them all play nice. And then we're going to kind of draw some conclusions at the very end. So first, walking through what it takes to build a single library. So the first step, of course, is always acquiring the sources. There's pretty much two generic ways to acquire sources. There's Git, and then there's just doing a direct HTTP download of some kind of zip or tar.gz or what have you. In CppCon, what we found is that doing that direct archive download is actually for the better. So most hosts, such as GitHub, GitLab, Bitbucket, Fabricator used to have issues, but I think that they fixed them. They all provide direct tarballs of a particular commit. What this means is that you can download just the code you need, and you don't have to clone every mistake that was ever made in the entire repo, right? So that's pretty good. So we tend to prefer direct archive downloads. This also allows us to perform a very effective hash. It's a very straightforward system, a very uniform system, because some people are Git, some people are not Git. If we use these direct archive downloads, then everything goes through the same system, and we perform a SHA-512 hash check of that source code so we can guarantee that this is not going to change and that you get reproducible builds day in, day out, tomorrow, in the rain, upside down, etc. Unfortunately, we already run into problems. So the first problem is that some library authors change their tags after they publish them. So they tag v1.0.0 and they'll push that to GitHub, and that's great. But then, an hour, a day goes by and they think, there's an issue in that release. A customer just reported a bug, there was a regression, and well, it's fine. I'm just gonna update the tag, it'll be fine. That's not okay, right? That's not okay for you as a consumer. That's not okay for libraries to be silently updating out from underneath you. So in CppCon, we have, as I mentioned, we have SHA-512 hashes on top of all of the source code. So this guarantees that if someone was to try to change something maliciously or benignly, as is most of the cases, that it will be caught. And then you can actually decide what the appropriate action is in your particular case. Maybe it is to redirect to an archive of that previous version that you were already using, because maybe that's what you're using in the field and you can't change it at this time. Or maybe it's simply to upgrade to the newest version, but now that you've acknowledged that changes have been made. However, what we found is that probably the best way to handle this is to directly access Git commit IDs. So the first point is that you should prefer Git commit IDs as your point of truth, because that doesn't change. This seems obvious, but a lot of systems are predicated on using the human readable name, the tag, as the reference identifier, and the problem is those are not truly stable. Unfortunately, preferring the hashes sometimes breaks, or preferring archive downloads sometimes breaks down, because there are hosts which actually have different hashes every time you download them. So GoogleSource.com, for example, which Android's source code is hosted here, along with many libraries that are developed as part of Android that one might want to use outside of Android. Those archives are created on demand, and they're tar.gzs, and they have embedded timestamps, And their particular method for producing these uses the current time for some of those timestamps, which means that every time you go to download that tarball, it changes the hash. So you can't actually easily guarantee that you get the same source code every single time. In CppCon, what we've done in this case is we've fallen back to doing the git clone, which means that for this particular library, it does act differently than everyone else, which causes pain in management of the system, because consistency is king here. Once we've got the source code, we introduce our most powerful weapon, which is patching. Fundamentally, that is what enables us to do anything that is required. At the end of the day, we can completely replace the source code if that's what is necessary to make things build. But this is the ladder that goes over any wall that the upstream maintainer may accidentally introduce. So now, right before we build, we do need to make sure that we have all of our dependencies available. So in CppCon and in most systems, you will have already transitively built and installed any necessary dependencies. So if you have something like, say, you're trying to build CppRest SDK. So CppRest SDK is a library that I used to work on. It depends on Boost. So we have to download and acquire Boost and install it and make it available in the same way that it would be available for a consumer. We have to make it available for the particular build of CppRest SDK. This is kind of obvious for libraries. However, for tools, things are a little bit more complicated, and there's a little bit more flexibility in what you need to do when a library says, oh, you have to build this inside of MSys, like FFmpeg does. Or, oh, you need to build this with Perl, like OpenSSL does. Or you need to have a copy of Python with this particular module pip installed so that our code generator can run. Well, we think it's unacceptable to modify the system state in that way underneath the user. I don't think that using a package manager for C++ should silently pip install things on your system. Maybe that's a personal opinion, but that's not what CppCon does. So instead, what we prefer to do is we prefer to get isolated copies of these tools as much as possible. So for example, on Windows, we'll download a private copy of Python that we can then do this pip install for. We'll download a private copy of Ninja, of CMake, of Perl, of any tools that we can, so that we can make sure that these builds are absolutely 100% reproducible from machine to machine, from day to day. Now we get on to actually doing the build. So there are many different build systems in place today in various libraries. However, in CppCon, in practice, what we found is that the vast majority of our libraries either support CMake primarily or secondarily. So this means that, again, consistency is king. If we make CMake work, then most libraries actually do just work. Unfortunately, this isn't the only case. Also with scale, you hit edge cases. You hit edge cases where they don't have CMake. They have the aforementioned bash script or the Perl script or the custom build system that is really only used by them, or the build system that they published as part of producing that project but doesn't necessarily have enough adoption. Or you have new build systems that are still somewhat immature and are still growing into possibly delightful things in the future, but right now that can sometimes be painful to work with. So at scale, of course, this means you don't want to write the individual, execute process calls for every single library every single time. You build helpers. That's what we do. We build functions that wrap particular kinds of build systems. But similar to how there's varying levels of adoption, there are varying levels of quality in how these wrappers can work. As the most compelling example, you have things like toolchains. How do you specify what compiler to use? CXX environment variable, that wasn't that hard. How do you specify what compiler flags to use? Well, CXX flags, still not that bad. How do I specify that the platform that I'm targeting produces executables that end in .js? That's a little bit more difficult. CMake has a mechanism to do this, and I'm sure that other build systems have a mechanism to do this as well, but there is no genuine wide consensus on how to specify this in a way that is agnostic to to the underlying build system. This is the fundamental problem with toolchains. If you crack open a CMake installation on your machine and you look through kind of those platform files, there's an enormous amount of code that goes into defining exactly what a target looks like. So the hope that we can define it in just a handful of environment variables seems not really workable from the very start. So this is where you get varying levels of quality that are more and less difficult to control. So toolchain files, CMake has a bunch of those, and if you, as a user, provide a toolchain file, then that means that we can make CMake behave as you intended. But how do we make FFmpeg deal with that? How do we make FFmpeg work the way you intended? We have some strategies, and I'll get to those in a moment. But I'll also say that with these helpers, with certain build systems, we also know what form the standard parameters for that particular system. So with CMake, for example, there are a bunch of standard flags that you can pass, such as CMake install prefix, CMake install bindir, CMake install libdir, build shared libraries, etc. By knowing these standard variables, what this means is that we can more easily handle libraries that we've never seen before. This means that porting a new library, adding a new library to the ecosystem is infinitely easier when it is one of these build systems that we already have a helper for that has well-established conventions for the way that things are done. So what do we do in these worst case scenarios where a user has, say, a custom Python script that is hard-coded to use GCC, for example, and we want to enable users to use Clang or, God forbid, MSVC? So honestly, most of the time in these cases, the easiest answer is actually to replace the build system when they're this problematic. This is because, in fact, the vast majority of libraries actually, from a package manager's perspective, really do boil down to just star.cc. So we embrace globs, and we rewrite the build system. With CMake, honestly, if you are pragmatic about it, if you are focused on the task at hand, which is delivering the build in a reproducible, reliable way that consumes dependencies correctly from the rest of the system, these are very easy to write. 30 lines or less, even. It's actually quite easy. So while it seems drastic to say replace the build system, frankly, replacing the build system is less lines than the patch file that would be required to make the original build system work. And the build system replacement, you know what conventions it's using. You know that it's going to respect build shared libs. You know that it's going to respect find package. Whereas in the case of a dozens or hundreds of files of build scripts, you don't necessarily know that. However, replacing only really does work effectively if it is that short, if it is that simple. There are libraries that are not, and these are really important libraries that we really want to use. Things like Qt, things like Boost, things like CMake itself. No, withdrawn, sorry. Things like LLVM. These really complicated libraries, we can't just replace them when we find a problem. In the cases where they're using a build system other than one of the ones that we have first-class support for, and we really do want to make that toolchain scenario work, where we can specify things like how exactly should you pull in a dependency library? What are the transitive requirements of that dependency library, and how are those encoded in the system? When you have to extract all of this information out from what the user has provided and what other libraries have provided, and there's problems in the existing build system, one approach that we can take is we can actually wrap the existing build system in another build system. So this is not a replacement. This is instead effectively adding a second configure step that runs ahead of time. So a 0th configure step, which pulls in all of the information specified by the user in a, say, CMake toolchain file. This way, the user only needs to specify things in a single place. We pull all that information in, and then we can pass that in a build system specific form to the underlying build system. In CppCon today, we actually do this in 2 cases. We do this in Boost to construct a bjam user config. So bjam is Boost's build system today. They are looking at moving to CMake, but I'm sure that that's going to be a multi-year endeavor. So for now, we continue to use bjam. But the problem with BGEM, of course, is that its particular toolchain format is used by only the people who use Boost build and BGEM, which is, for the most part, just Boost. So that means that users, it's a bit, you really can't expect users to provide a user config file or a user config.gem file, which is the name of the toolchain file for BGEM. You really can't expect users to provide that file for every possible build system that we package. So instead, we run a CMake build on top. We gather information such as the compiler flags that have been set by the user, the runtime that has been set by the user, the compiler that is being used by the user, other environment variables that are being used by the user, the names of the libraries that will be pulled in, because we can run find a library in CMake, or we can run find package, and we can kind of extract that information out. And then we push that and we generate a toolchain on the fly for the underlying build system. We also do this for OpenSSL. OpenSSL uses Perl, and it takes its particular parameters in a certain different way. And what this results in is that this enables us to build Boost and OpenSSL with the Android toolchain built inside CMake by simply setting the CMake system name and selecting the Android toolchain. We're actually able to use all of that incredibly expensive to develop detection logic of what NDK version you're using, what STL version are you using, et cetera, reusing all of that to then build these libraries which don't support CMake today. So this is a powerful technique, but it's also incredibly difficult. We're only using it in 2 cases today, but we will probably need to use it further in the future in order to improve support throughout the ecosystem for custom toolsets. So there's a few different ways that libraries can ask for their dependencies during their build. One is package config. This is popular on Unix platforms. It's used by AutoConf, it's used by Meson, and it's used by many other build systems. Even hand-rolled make scripts can use package config. Other build systems will do direct library name references. They'll just effectively hard code either a -l name, or they have some other facility which morally is adding just a library name to the linker line. MS-build in particular for us this is the primary way to add dependencies to MS-build, is to have a list of library paths to search for, effectively -Ls, and then the individual libraries to link -Ls. In CMake, you have find package and find library. Find library acts very similar to this direct library name reference. It has a little bit of fallback logic inside of it, which is very nice. But find package is really the preferred method, and that works more like package config. So both of those systems, find package and package config, let you declare a dependency on a package by name, on a more complete understanding of what it is, more than just its library name. So this includes headers, this includes potentially configuration flags that you need to pass to your compiler, and most importantly, it contains transitive dependency information. In find package in specific comes in kind of 2 flavors. There's 2 ways that a find package call can be resolved at runtime. One flavor is config files, which are intended to be provided by the project, and the other flavor is find scripts, which can either be provided by the consumer. So just to clarify, the config files are provided by the producer. So find scripts can be provided by the consumer, or they could be built into CMake itself. These are incredibly popular and widely used, both of these. So there are a bunch of libraries that provide config files. There are just as many libraries that don't provide config files. And CMake has a bunch of find scripts for what you consider to be critical to build software. Things like Boost, things like OpenSSL, things like libxml2. These things are provided by CMake itself to help bootstrap the ecosystem once upon a time, and they're still around, and they're still widely used, and they still work. However, this isn't perfect, right? It's not error-free. So the 2 most common issues that we have in a find package call, things that can break down here, one is that the libraries themselves are not specifying all of their dependencies correctly. So this happens, unfortunately, in the case of find XYZ scripts provided by CMake itself. And this is because CMake really can't do the right thing here. CMake doesn't know the particular ways that the library that you are consuming was built. It has to make a best guess. It doesn't know that curl was built statically with OpenSSL or not. So therefore, it can't know whether it needs to transitively go and try to find OpenSSL. It just tries to do its best effort. It finds curl itself. It links curl and hopes that that's all you needed. And if you needed more, then sometimes you will have to go and explicitly find package those yourself, or we can fix it in one place. So in CppCpackage, what we do is that we actually are able to hook find package. This is not using a public isn't the right word. This isn't using a preferred method in CMake, and we're looking for better alternatives. But for now, what we found to be highly effective is that we actually hook find package itself. And what this lets us do is it lets us do the normal resolution, fall through to the find script underlying that particular call. But then on the way back out, we can fix this issue. We can add additional dependencies to that dependency list. So we know that we built curl statically with OpenSSL. We know that this means you need to call find package OpenSSL in order to be able to use curl, and you need to add its dependencies into the dependency list to provide that transitive information. And so we do that. Another example that we run into problems is incomplete targets. So the way that CMake works with find package is you call find package, and then this can provide a list of targets. At least this is the modern CMake that we're trying to move towards, and is significantly better. I highly recommend it in general. However, it is possible that in a particular configuration, a library is not providing the same targets as it would in another configuration. The number one bad behavior here is static versus dynamic builds. A lot of libraries will provide a static target that's different than their dynamic target. So zlib-static instead of zlib as the target name. And in your CMake, that means that you have to choose which one that you depend upon, which means that somehow you need to intuit the way that the downstream library was preferred to be built. It doesn't work. It doesn't scale. That means that every single consumer needs to be configured in the exact same way every time, and if you get it wrong, bad things happen. So what we can do with this find package script is that we can paper over these sorts of issues. We can say, don't worry, zlib, don't build your static form, only build your dynamic form. And in order to make the libraries that try to use the static form work, what we can do is we can inject alias targets that alias back to the dynamic name. So we introduce the static name, but it actually resolves to the dynamic name. So this enables us to undo this decision point in the graph. And currently, we use this technique in 35 different places across our ecosystem. So 3% of libraries we need to fix. So we've managed to build the library. We dealt with all of its dependency problems. We patched whatever was necessary to patch. So now we have the binary artifacts coming out of the build system. So these need to be rearranged into a standard way so that we can provide further services on top. So this means things like, well, being able to build code on top of it directly. So we want all of the lib files to be in a certain directory. We want all the .a's to be in a certain directory. We want .so's to be in a different directory. If you built any tools, we want those packaged this way. If you provided integration files like package config or CMake scripts, then we want those to be in certain arrangement in a certain way so that we can do things like tell the user, hey, this library provided this kind of integration. Here's how you should take advantage of it. And in order to do that, we need things to be organized in a certain way. Furthermore, beyond just organization, we sometimes need to make some patches at this point because, for example, the files that you generated might have absolute paths in them. And relocation is not optional, it is a requirement. Being relocatable, having your binary outputs be usable either on a different machine or even in a different directory on the same machine is really mandatory. That's not an optional step. So the way that we can achieve this, often the easiest way to achieve this, is to replace in those files absolute paths with relative paths, and do this as kind of a generic regex. I will skip over some of these other for time to make sure that we have questions at the end. I mentioned static libraries and dynamic libraries before, but in addition to simply needing to patch the consuming side, this usually takes several steps to resolve if a library is designed to provide both static and dynamic at the same time. We'll have to patch the original build to make sure that they have an option to only build one of them. We'll need to patch the headers post-install to make sure that any macros in this configuration state, curl underscore static needs to be defined if you're consuming it statically, or zlib underscore static maybe needs to be defined, or what have you. We may need to patch the headers post-install to make sure that downstream consumers are getting the right macros. And then finally, we may need to intercept things like find package in order to make sure that if someone is depending on zlib static, and we've chosen, or the user has told us that, no, I want the dynamic zlib, we need to make sure that that resolves correctly, which in the case of zlib static would mean resolving to the dynamic zlib. So those were a summary of some issues that happen when you look at mostly a single library in isolation. But there are additionally techniques around how to manage the ecosystem as a whole. And probably the most important of these is how do you upgrade? Package management is not just a point-in-time problem. It's really a problem over time, and a question of how can you stay up to date, how can you resolve CVEs quickly to ship good, robust software. So at scale, you can't assume Semver. Any system that is dependent upon Semver really can't work at beyond a certain scale. Yes, any of the libraries that you produce, I highly recommend you take a look at Semver and you see if it makes sense to you and adhere to it if you can. But in general, if you are packaging other people's code, you cannot assume Semver. So instead, what we do is when we want to upgrade something, we build everything. We build everything and we make sure that they still work. And that's much more powerful than Semver can be, because Semver is intentionally much lossier than that. Just because Boost has said, I broke an API, which they do every time, that doesn't mean that other libraries fail to build. Secondly, is the title of this slide, Upgrading Everything Together. The realities of software development today is that you are testing against a finite set of versions for your dependencies. And one of those versions, I hope, is the latest. What this means, though, is that your latest version primarily is tested against the latest version of your dependency. And they are tested against the latest version of their dependency. And they're tested against the latest version of their dependency. So what makes you think that you can take one of these pieces and upgrade it without upgrading everything else? And the answer is you really can't at scale. So this is why in VC Package, again, we do upgrades together. We move every library forward at the same rate. And we discourage pinning, though, of course, in specific instances, pinning is always a necessary fallback. But the happy path, the optimal path, the path that produces the best results is upgrading everything together. Additionally, when we do these upgrades, we want the ecosystem to still function. We need the ecosystem to still function. And what this means is that we need to address regressions then and there, because otherwise you end up with broken diamonds. Broken diamonds are the case where you, your library, may depend on an A and a B. And A and B both use Boost, but they use different versions of Boost because Boost released a new version and someone didn't fix B. They just released the new version of Boost. So B tries to get the old version of Boost, and as long as you're only using B, then this is fine enough. This is fine enough. You get the old version of Boost. But as soon as A decides, I'm going to move my testing forward to the new latest version, right? That's what we do as good software developers. The new version literally has CVEs out. It has security vulnerabilities against it. I cannot responsibly continue to ship the old version. B still isn't updated. So then if you want to use A and B, your software has a problem. You can't upgrade to the new A just because of Boost here. Because they took a dependency on the new version of Boost. So this is why managing everything together in a centralized repository really is the best way to scale this particular problem. So we can ensure that we push regressions all the way, we can push regressions out of the system as we go through. So it looks like I'm out of time. I'm so sorry that I was unable to reserve enough time. My voice is going out already. But I'm going to skip to the end and just go over two brief conclusions. First is that oftentimes the problems that you need to fix are root caused in the producer. And the best way, the sound engineering practices, is to fix it in the producer and not do workarounds in all of the consumers. This is just obvious. Prefer the order 1 solution than the order n solution, right? And in order to do that, that means you need a single consistent view over the entire world. And the second point is simply that problems are repeated. And with all of these techniques that I've mentioned, this is what we're able to achieve in VC Package. We've got over 1,000 libraries on Windows, 850 on Linux, and about 800 on Mac, and it's increasing at a rate of 1 per day. So thank you.